Hello class, I hope you're having a wonderful day. Today I would like to complete a practice problem with you involving a position time graph. So I'm going to read the problem to you and then we can go ahead and get started. So a bus travels on a northbound street for 27 seconds at a constant velocity of 13 meters per second. After stopping for 20 seconds, the bus travels at a velocity of 16 meters per second for the next 40 seconds to the next stop, where it remains for 18 seconds. For the next 16 seconds, the bus continues to move north at 15 meters per second. So in part A, the problem wants us to construct a position time graph. So whenever we say a position time graph, we are describing the position. This is our dependent variable, so our dependent variable goes on the y-axis, and time, position time graph, the time is our independent variable and it's going to go on the x-axis. So our position will be in units of meters. And as you can tell, I've gone ahead and written a scale down here. The scale that I'm using is 100 meters. And so we're going to start at a position of 0 meters. And I've got marked on my y-axis 1,300 meters. So my independent variable is time. So let's go ahead and write time. And our units for time are in seconds. And my scale is 10, so I'm starting at a time of 0 seconds. I'm going up by tens on my x-axis all the way through 130. And like I said, we're in units of seconds. So for part A, it says construct a position time graph for the motion of the bus. So let's go ahead and look at the first sentence. It says, a bus travels on a northbound street for 27 seconds at a constant velocity of 13 meters per second. So, at a time of 0, we are going to be at a position of 0 meters. So we're going to, our first ordered pair will be on the origin. Now, what we want to do is calculate the position of the bus after 27 seconds when it's traveling at 13 meters per second. So what we're going to do is use the equation d sub f, this stands for the final displacement of the object, is equal to our constant velocity multiplied by our time interval plus d sub I. This is our initial position or our initial displacement. So our initial displacement for our first scenario here, we are starting out at a position of 0 meters. So this guy goes to 0. We don't need to mess with it anymore. So my constant velocity is 13 meters per second. We're going to multiply this by the time interval. So this is how long we're traveling at 13 meters per second. And we're traveling for 27 seconds at this velocity. Okay? So before we calculate this, we can immediately see that the units of seconds will cancel. I have units of meters per second times seconds. And algebraically, we can write this as seconds over 1. So I have seconds in the numerator and seconds in the denominator, and those will cancel, leaving us with units of meters. So let's go ahead and take out our calculator. 13 times 27, we get 351, and we have units of meters. Okay, so we need to identify our next ordered pair here. So 27 seconds, let's locate 27 seconds on the x-axis, and we're now at a position of 351 meters. So somewhere about right here, okay? And let's go ahead and connect our ordered pairs here. what I want to do, each time I place an ordered pair on the graph, I'm going to identify that ordered pair with correct units. So, our ordered pair, you know, we always start with the x value first. We are at 27 seconds, and my y value is 351 meters. Okay? So my point, 27 seconds, 351 meters. Okay, next. It says that after stopping for 20 seconds, okay? So if we stop, if our velocity is 0, we are not changing position. So 27 seconds plus 20 seconds is going to be 47 seconds. So our next ordered pair will be 47 seconds, 351 meters. And so that means we are, here, let me write this down, 47 seconds. At 47 seconds, we are still at a position of 351 meters with respect to the origin. Okay? All right. So after stopping for 20 seconds, the bus travels at a velocity of 16 meters per second for the next 40 seconds. So once again, we're going to use our equation. V sub f is equal to v bar times delta t plus d sub I. So our constant velocity this time is 16 meters per second, and we're traveling at 16 meters per second for 40 seconds. And we have this plus d sub I, and this is our initial displacement, so this is the displacement with respect to the origin. So right now we are at a position of 351 meters, and we're north of where we started, so plus 351 meters. So let's grab our calculator again. 16 times 40 is 640. So once again, our units of seconds cancel. So I have 640 meters plus 351 meters. And we can add both of these values since they have the same units of meters. So this is going to be 991 meters. Okay? So right here, we stopped for 20 seconds, so we did not change our position, and then the bus traveled at 16 meters per second for 40 seconds. So we're at 47 seconds plus 40 seconds, that's going to be 87 seconds. So I can place a mark right here and say 87 seconds. And now we're at a position of 991 meters. So 991 meters is somewhere about there. And I'll go ahead and identify my ordered pair. We're at 87 seconds, 991 meters. Okay? To the next stop. So at the next stop, it remains stopped for 18 seconds. Okay? So what we're going to do is 87 plus 18 is going to be 105. And so at 105 seconds, we are still at a position of 991 meters. So 105 seconds, 991 meters is my ordered pair here. Okay, then it says for the next 16 seconds, the bus continues to move north at 15 meters per second. Okay, so d sub f, so our final displacement is equal to v bar delta t plus d sub I. So our velocity is 15 meters per second times 16 seconds plus the initial displacement with respect to the origin. So we're at 991 meters. All right, so 15 times 16, is that 240? Yep, 240. And units of seconds cancel. So 240 meters plus 991 meters gives me 1,231 meters. So 16 seconds, we're at 105 plus 16. My next ordered pair, or I should say my last ordered pair for this problem, is going to be 121 seconds, 1,231 meters. Okay, so 121 seconds and 1,231 meters. That is my last ordered pair. Okay? All right, so we're done with part A because part A wanted us to construct a position time graph, and we've done that. We've labeled both axes, we've generated a scale, and we've plotted all of our ordered pairs for position and time, and we've also labeled each ordered pair. So we're doing good on part A. Let's move on to part B. What is the displacement of the bus? Now remember, there is a difference between distance and displacement. Distance is a scalar value and it only describes the magnitude. But displacement is a vector and it's going to describe direction and magnitude. So the problem tells us that the bus is traveling on a northbound street. So for part B, what we can do is say, what is the displacement of the bus? We can take a look at our position time graph, and it's 1,231 meters. So our final displacement, 1,231 meters. Now, if we leave it like this is just distance. So displacement is a vector. We're required to describe the direction, and we can say north. Okay? So that's part B. Now part C, it asks us, what does the slope of the line represent on a position time graph? So the slope of the line is this guy here. We're describing the rise over the run, okay? So on a position time graph, the slope of the line represents the object's velocity. And so I'm going to go ahead and write that down, but then I want to prove that calculating the slope of the line here. So we can say the slope of the line on a position time graph represents the object's velocity. And I'm going to underline that there. All right? So the slope of the line on a position time graph represents the object's velocity. So we can prove that right here. So we know the slope of the line identified by lowercase m can be calculated delta y divided by delta x. So remember this capital Greek letter delta here means the change in. So the change in y divided by the change in x, this is going to be y2 minus y1 divided by x2 minus x1. So y2, so this is my first ordered pair. We're going to use this as our second ordered pair because we're going to calculate the velocity of the bus during this time period here. Y2, well, here we have 351 meters. So 351 meters minus y1. Well, remember that we started at the origin, so minus 0 meters, divided by x2. We're at 27 seconds. minus x1, well, we're at the origin, so 0 seconds. We can do 351 divided by 27, and this gives me 13. Now let's take a look at the units. In my numerator, I have units of meters, and in my denominator, I have units of seconds. So, there we go. Our velocity is 13 meters per second for this time interval of 27 seconds. Now, let's take a look at the problem. Our problem tells us that a bus travels on a northbound street for 27 seconds at a constant velocity of 13 meters per second. And we checked our problem by calculating the slope of the line here. There we have it, 13 meters per second. All right, well, I hope this problem has helped you today. If you have any questions, you can give me a call or send me an email. I will be more than happy to help you. I hope you have a wonderful day.